Hello guys, my name is Mohammed. Today we are going to talk about three-phase induction motors. Three-phase induction motors widely used AC motor to produce mechanical power in industrial application. Almost 80% motors in industries three-phase induction motors. That's why it's too important for us. So, if you want to check equivalent circuit of three-phase induction motors, we have R1, which is winding resistance of stator, and we have X1, which is inductance of stator winding. We have RC, which is core loss, and we have XM, which is magnetizing reactance of winding, and we have X2, which is rotor winding resistance referred to stator winding, and at the last part we have R2 divided by S, which is power of the rotor, which includes output mechanical power and copper loss of rotor. In three-phase induction motors, we have two main parts, which is stator and rotor. Stator is our stationary part of motor, and rotor is our rotating part of motor. Stator, we have three parts: stator frame, stator core, and stator windings. Stator frame is outer part of our motor, and it supports stator core and stator winding. Stator core is scalar alternating magnetic flux. In rotor, we have shafts, we don't have brushes, we have laminated iron core, aluminum ring, and bars. So, the operating principle of three-phase induction motor is based on the production of rotating magnetic field, which is RMF. The stator of induction motor consists a number of overlapping windings offset by an electrical angle of 120 degrees. When the primary winding or stator is connected to three-phase AC supply, it establishes a rotating magnetic field which rotates at a synchronous speed. The direction of rotation of the motors depend on the phase sequence of the supply line and the order in which these lines are connected to stator. Interchanging the connection of any two primary terminals to the supply will reverse the direction of rotation. The number of poles and the frequency of applied voltage. The rotating magnetic field in stator is the first part of the operation to produce a torque. The rotors must be carrying some current in induction motors. This current comes from the rotor conductors. The revolving magnetic field produced in the stator cut across the conductive bars of the rotor and induce an electromotive force, which is EMF. The rotor windings in an induction motor are either close to an external resistance or directly short. Therefore, the EMF induced in the rotor causes current to flow in a direction opposite to that of the revolving magnetic field in the stator, and it leads to twisting motion or torque in the rotor. As a consequence, the rotor speed will not reach the synchronous speed of the RMF in stator. If speed match, there will be no EMF induced in the rotor. No current will be flowing, and therefore no torque would be generated. The difference between the stator, it means synchronous speed, and the rotor speed, it's called the slip. So, for slip, we have formula, which is ns minus n divided by ns. ns means synchronous speed, and n means rotor speed. For finding finding ns, we have also one formula. It's ns equal to 120 multiplied by f divided by p. F is supply frequency of our motor and p is number of pole on the stator. A three-phase induction motor is self-starting. When the supply is connected to stator of the three-phase induction motor, a rotating magnetic field is produced and the rotor begins rotating and induction motor starts. At the time of starting, the motor slip is unity and starting current is very large. The purpose of starter is not just to start motor, but it performs two main functions. One is to reduce the heavy starting current, other one is to provide overload and undervoltage protection. The three-phase induction motor may be started by connecting the motor directly to full voltage of the supply. The motor can also be started by applying a reduced voltage to the motor. The torque of the induction motor proportional to the scale of the applied voltage. Also, greater torque is exerted by motor when it starts on full voltage than when it starts reduced voltage. Three starting method. First one is direct online starter, second one is star delta starter, and third one is auto transformer starter. So, direct online starter method of induction motors is simple and economical. In this method, starter connected direct to supply voltage. By this method, small motors up to 5 kW rating are started to avoid the supply voltage. Then, second one is star delta starter. The star delta starter method of starting three-phase induction motor is very common and widely used among all the other methods. In this method, the motor runs at delta connected stator windings. And last one is auto transformer starter. Auto transformer starter is used in both types of connection, either star connection or delta connection. The auto transformer starter is used to limit the starting current of the induction. So, let's talk about speed control. The speed of induction motor can be controlled by stator and rotor side. From stator side, we can change applied voltage, applied frequency, number of stator poles. From rotor side, we can change rotor resistance and injection EMF in the rotor circuit. If we check from speed control from stator side with changing applied voltage, from the torque equation of induction motor, the torque is directly proportional to scale of applied voltage. The slip at maximum torque is independent of the applied voltage. And also, the change in supply voltage does not change the synchronous speed. So this method, if the voltage are varied more than the rated voltage, it will result in magnetic saturation and it may create some problems. In the worst condition, the core of our motor will damage. With a reduction in supply voltage, developed torque reduced gradually. The range of speed control is very limited from rated speed to lower value speed. From all reasons, we can conclude that speed control by voltage variation is not popular to large motors, but it can be employed for very small motors. So, let's check from changing frequency and number of poles. So if we change the number of poles and frequency, we can change the synchronous speed, and so on. We can change the rotor speed. Now, for constant value, if we change frequency, the flux is also changing. And to have adequate overload capacity, the motor should maintain constant flux through the speed control. Therefore, only frequency control is not adequate for induction motors. The flux will remain the same if Vf remains constant. So, it's become necessary to control the supply voltage and frequency to make a ratio constant. This method, known as Vf method of speed control. When we want to change direction of rotation, we have to choose two terminals connections with any two input voltage terminals of motors. This will reverse direction of rotation of rotating magnetic field in their air gap, and motor will rotate in reverse direction. As you can see in this picture, when we change L2 with T3 and L3 with T2, it's going to be reverse the direction. So, the power factor of induction motors with load typically from around 0.85 or 0.90 at full load, as low as about 0.20 at no load. At no load, an induction motors draws a large magnetizing current and small active component to meet the no load losses. Therefore, the induction motor takes a high no load current lagging the applied voltage by a large angle. Losses in motor directly affect the cost of operation and motor rating. The efficiency is frequently determined by calculating the loss. As you can see, the formula is efficiency is that one. P out divided by P in multiplied with 100.